So as we were talking about how these ions form their structures to make ionic compounds, we had talked about the formula unit, and that's the attraction of those positive and negative cations towards each other. Now, just like we had learned back with periodic trends, the attraction between oppositely charged particles is controlled by Coulomb's law, or is modeled by Coulomb's law. So what we can infer from that is that as particles have larger charges or get smaller, the attraction between those two ions are going to become larger. And that's going to play a lot of different unique properties for ionic compounds compared to something like water or other covalent compounds. Now, there's a lot of stuff going on in this diagram, but really what I'm trying to focus on here is just this shows how much energy is needed to separate the two ions in barium oxide and cesium fluoride. Now, what we see here is we're comparing barium to cesium in terms of the cations, and both of those have the same number of energy levels. The difference is that barium loses 2 electrons to make a 2+ ion, whereas cesium loses 1 electron to make a 1+ ion. For the anion, we have oxygen and fluorine, which have equal numbers of energy levels as each other, but one's a 2- charge and one's a 1- charge. In looking at the graph on the right, we can look to see this red arrow here. This red arrow represents the change to go from the compound to the separate ions. If we look at the labels on the two sides of those arrows, that represents this amount of energy referred to as the lattice energy, and it's the amount of energy that gets released when those ions come together to form the crystal. And we see that when cesium and fluorine come together, it releases about 760 kilojoules. But when barium and oxygen come together, it releases about 3,050 kilojoules. The energy released when the barium and oxygen come together is about 4 times greater than that of the cesium and fluorine, meaning they have a much stronger attraction towards each other and they come together much more readily. This actually perfectly models the equation of Coulomb's law too, with the 2 charges on top and the distance on the bottom squared. Like we had said before, barium and cesium have the same number of energy levels, and so do oxygen and fluorine. So the relative differences between these two ions from one compound to the other are pretty insignificant, leaving just the 2 charges there on top. Well, the force for cesium and fluorine then, I'm going to put my S where it's supposed to be. We had a +1 charge on the cesium. We had a 1- charge on the fluorine. So we have a charge of -1, meaning that the negative sign means that it pulls together. Whereas if we do the same exact thing for barium and oxygen, we see that we had a 2 positive charge. We had a 2 negative charge. So the force between them is -4. So the force is about 4 times greater, which means it should require about 4 times as much energy to pull those things apart. That difference, right, the amount of energy required to break them apart is going to play a big role in different properties. One of them being just the fact that ionic compounds themselves are generally really hard, right? The crystals have a hard structure, unlike something like charcoal or carbon or oxygen, which is a gas, right? The crystals themselves are hard, but if enough force is applied to them, for example, if you hit them with another rock or a hammer or something like that, they tend to shatter. They're very brittle in that sense, and they'll fracture into different pieces. And the reason this happens is because if we apply a force to these crystals, like this arrow is indicating here, and we shift all of them over a little bit to the right, we see that now we have 2 ions of the same charge next to each other, which when we were talking about forming the crystals in the first place, we said that doesn't happen because those would repel. Well, the same thing happens here. If enough force is applied to shift them just a little bit over so that they repel each other like that, these 2 pieces are going to fracture and split apart very, very readily. Another property that this plays a role in is something that we have talked about a little bit already back when we were doing crystals, is solubility. From the solubility curve here, I pulled out a couple different compounds, one of them being potassium with iodine called potassium iodide. We have sodium chloride, and then magnesium oxide, which isn't even on the chart because it doesn't dissolve at all. Now, why do these three things have such varying differences in terms of how well they can dissolve? Well, we need to keep in mind that when an ionic compound dissolves, the positive and the negative ions are going to separate from each other. So in the case of potassium and iodine down here, it would split up into the K1 plus and iodine 1 minus ions. Sodium chloride would split up into sodium and chlorine. And magnesium and oxygen, if it did split up, would have to break up into magnesium and oxygen ions. Now, magnesium and oxygen have a 2 positive and 2 negative charge, which means the attraction between those two is going to be significantly higher than between the potassium and iodine or between the sodium and the chlorine. And that really strong attraction there means that it's going to take a lot more energy to break up these two ions from each other compared to the first two. And this is why water cannot dissolve magnesium oxide, because it doesn't have enough energy. It's not strong enough to pull those two ions apart from each other. However, water can dissolve these two compounds, potassium iodide and sodium chloride, but it can dissolve one easier than the other, even though they both have the same charges, because they aren't the same size. Right? We know that distance plays a factor in attraction. Potassium has 3 energy levels once it loses that 1 electron, whereas sodium only has 2 energy levels. Right, so that smaller radius means that the sodium ion can get closer to the chlorine than the potassium can to the iodine, leading to a stronger attraction over here because of the smaller size. And that stronger attraction means that water is going to have a more difficult time dissolving it compared to the potassium and iodine. Another example of how the strength of attraction plays a role is looking at how much energy is needed to boil or melt these compounds. We see that for ionic compounds, we need to have extremely high temperatures to melt them into liquids or boil them and turn them into gases, much, much higher than room temperature. For example, water, we know our covalent compound with one of its really high melting points and boiling points, boiling at 100 degrees Celsius. To melt even a weakly attractive, to boil a weakly attractive ionic compound, we're upwards of 1,000 degrees Celsius. And that's because unlike water, where we have our individual molecules with just the hydrogen bonding interacting between one another, right? But it's not really a chemical bond, it's just an attractive force. The ionic crystals have that positive and negative attraction in every direction, holding them all together. So a large amount of energy is going to be needed to overcome all of those different attractions, keeping them in place. But even when it does, we see that there's big differences between different ions. We see that something like magnesium and oxygen with its 2 plus, 2 minus charges, compared to potassium and bromine with its 1 plus, 1 minus. We see that we need a lot more energy to melt the magnesium oxygen, or to boil them. And lastly, one other thing that's unique to ionic compounds is that when they do dissolve, they conduct electricity. They make what are called electrolytes. So whenever you hear that word in Gatorade commercials, it's referring to all of the dissolved ions that are in the Gatorade. Because ionic compounds dissolve into the two ions, we now have mobile charged particles. So usually we refer to electrons like in a metal wire, which is what allows the metals to conduct electricity. But since we have ions that are dissolved and they're freely flowing around the liquid, if we apply an electric current to them, such as here in these diagrams, the electrical current comes in and it causes those ions to move around in the solution. So it allows that current to continue through the solution and then back out the other wire. So in this case, we see that because that current continues up, it causes the light bulb to light up. So in a solution here, where we have dissolved sodium and chlorine, we get a nice bright solution with a highly conductive solution. But if we do the same thing with sugar, which we know is a covalent compound, we don't see any of the light turn on at all. Similar to just plain water where there are no ions, we don't have any conduction happening. We don't see the light bulb turn on either. So in order for the electricity to flow, we need to have this mobile carrier. So if the ions do dissolve, we get this conductivity. If we were able to melt them, so that they were a free-flowing liquid at the 800 or 900 degrees Celsius that it said it required, it would be conductive as well. But as a solid, this doesn't happen because as the electrical current comes in, all of those ions are locked in place. They don't conduct the electricity, they're not allowed to flow. So the circuit is never completed and the light bulb can never go on.